Good morning. Not a huge crowd, but maybe you'll see me later, you other people out there, virtually, so that's also okay. Please remember, as I've written already, to evaluate the course, even though I know it's a bit boring, and you're probably fed up with all the evaluations you have to do across all the courses. But please do it anyhow. It's really being used, it's really being looked at, not only by me, but also by the local authorities who are looking after that everything is going on okay at our courses. So the local study boards, the local management are actually looking at all your evaluations of the courses. So it's both something for the teacher in person to improve on his work, to get good ideas of how to improve future courses, to correct things that you might have to correct, that you are not focusing on when you are stressed in front of 200 people. And as I said, it's being looked at by DTU in general. So please do it. Today, the topic is what we call, funny enough actually, as it will be clear soon, it is called analysis of variance. It is chapter 12 in the book, or the part of chapter 12 that we will be looking at. Here's the plan for today. We have two versions of it. We have the one-way version and we have the two-way version. I spent most of the time on the one-way version. And then we generalize it to the two-way, and in fact there are courses out there that will take you to 3, 4 and higher order ways. Not in this course. So it's just also to say this is a few steps in a direction where you can take more steps. Funny enough, so basically, I mean, we will spend 1.5 lecture time on the one-way and then sort of 20 minutes on the two-way, just to give you the idea of it. Let's go into it and try to realize what it's all about. Because funny enough, even though the name, the title of today's lecture is Analysis of Variance, what the purpose of today is really about is this question. Is there, in a grouped situation, having, for instance, 3 groups of data like this, 3 samples of this, coming from 3 different groups, or at least potentially different. We want to investigate whether they are really different. And the core of the investigation is really, funny enough, the means of the group. So even though it's called analysis of variance, just for you to state this right away, I'll repeat it, the focus of today is looking at the 3 means of the 3 groups and trying to compare those and find out whether they are the same or not. As such, today is the generalization of what we've seen previously in chapters 7 and 8, where we are focusing on comparing 2 means, right? We compared 2 means by a t-test back then. Today, and we did it in an independent way, and we learned how to do it in the paired or the dependent way. That is actually what we're going to generalize today. That is the one-way Anova, that is the independent. The two-way Anova, that's going to be the dependent. However, not only looking at 2 groups, but generalizing to more than 2 groups. And to use the most simple example of having more than 2 groups, I take 3 groups. But the procedures and the methods you will be giving works for K groups, right? Actually also for 2, and we'll get back to the link between the t-test and what we do today, which I say already now, it gives the same result, or it's the same thing. So, this is what we're going to do. And there are certain computations and certain thinking around doing this, what we do today. So today is statistics about the three means, how to make this hypothesis test about whether they are the same or not, and how to compute it, and how to interpret it, and how to do it, right? So, we begin with, taking you through some basic computations in this sort of very simple example, and then I give you along this way I'll give you the formulas, and then we'll sum it up in more general way of putting it a bit in some minutes from now. Basically, this is what it's all about. It's about comparing. I have brought some numbers here so that it's more easily done for me. We have an average in group 1, we have an average in group 2, and we have an average, let me just check to make the right sketch. The average in group 3 is 3.75. So basically, we have those three averages of the three groups. That's just computing the three averages. I hope you can follow me there. Something went wrong there. I know what. That was not the average we were looking at. Let me put it around here. Anyway, then we'll check whether it's okay or not later. These are the three averages that we are going to have a look at. Are they the same or not? That's the hypothesis we're going to check. How are we going to compare three averages? When we compared two averages back in chapter 7 or 8, we just subtracted them from each other and divided by something, and then we had the t-test, right? We had two, we subtracted them. We cannot do that with three. What can we do with three? Well, here is the solution. Let me again check what is the overall mean. I collected also in R the data into a Y column where I have these 12 data points, 4, 8, 12 data points. Let me just compute the mean of all those 12 data points. 5.23, right? That's the mean of everything. 5.23, that's around here, right? See if I can do it here. Whoa, it's not good today. Here, that's a straight line of, we call that the overall average being 5.23. Because this is the indirect way we're going to compare the three averages with each other, sort of the core measurement of how much are the group different, since that's what I'm actually doing now. I'm trying to measure how different are the groups from each other. I'm going to look at three numbers. This deviation, and this deviation. What have I put in here? I have taken each individual average and subtracted the overall average, like that, right? I've taken the three individual averages, subtracted the overall average. These are the three numbers I have here, here, and there, right? These three numbers. That is what I will call, if I take those three, I don't take exactly those, I square them, since negative deviations count in the same way as positive deviations to me. So I square these three, I go from 1 up to the number of groups, 3 in this case, k in general. And then I do one more thing. I use the information about how many observations are there in each group. Basically, I multiply by the number of observations in each group. In our case, Ni, for all three i's, I have only, Ni obviously is not 3, it is 4, and I have that the number of groups are 3 here, right? So let me try to compute this number, or even spell them out here. Let me give you these numbers for group A, B, and C. If we compute, we will see that group A, if we take the average of group A and subtract the overall average, we get, I tell you, we get minus 2.208 below. So we take the A average and subtract the overall average. If we take the group B average here, subtract the overall average, 5.23, I get a small positive number, as you could see from the picture. And if I take the C average up here, subtract the overall average, around 5, I get 1.52, right? So these are the three measurements. If all the three groups were exactly the same, right, they would be on the overall average, all three of them, and these three numbers would be 0, right? So exactly equal groups gives a number 0 here, and the more different the groups are, the larger these numbers, right? I call this number sum of squares of treatments. That's a generic name used in the chapter for this particular size here, statistic. Because it measures treatment differences, you could say, or group differences. Treatment is the generic term for the groups. You have in mind that you give different groups different treatments. That's why we use this word treatment. That is what is being done in agricultural experiments. That's what's being done in like medical experiments or clinical experiments with the drugs and things like that. So that's the terminology used for such groups here. SSTR, in our case, measuring how different the groups are in their means, then becomes 4 times minus 2.208 squared plus 4 times 0.667 squared plus 4 times 1.542 squared. And this number is 30 times 792. So the groups are 30 different. How much is 30? Is that big or is that small? Is that a big difference? Is that a statistically significant difference? How could we measure that? Yeah, that's what it's all about here. How can we measure that in a sensible way? What it boils down to is that we are lacking, or we are going to use some more information to evaluate whether the groups really seem to be more different than you can expect alone due to chance, right? If we look at the raw data again, let me see. Try this one. If we look at the individual data, you could also see how much are the different data varying within each group, right? Take each data point and see what is the difference between each data point and its own group mean, right? So we take the sort of the fluctuation, the scatter, the variability of data within each group, exactly like we did in chapters 7 and 8 with the two. We have one variance and the other variance. Now we have 3 variances actually, and we could look at those. And what are those numbers? Those small ones here, they would be each individual observation, and we need a double index now because we have 3 groups and then we have some numbers within the group. I denotes the groups, J denotes the observations within the groups, right? We look at how different are those individual observations from the mean that sort of belongs to the group from which the data point belongs, right? If we take those, that would mean that we would start computing. We would compute each yij minus yi. Let's, in fact, let's make sure that we get mean of the first 4 measurements, like this. That was the mean of group 1. What about the mean of group 2? That was 5.9. These were the numbers I was looking for from before. And the mean of the last three numbers, which is group 3, is 6.775. These were the three means that I plotted before. So mean of group 1, 3.025. I would take the individual number, which would then be 2.8 minus, I have I equal 1, 2, 3, and 4. And in fact, I have exactly 4 in each group. I could have different. Is there a question or just speculation? That's okay. Fair enough. 2.8 minus 3.025. I would take 3.6 minus this group average, and in the second group I would also take individual observations, 4 numbers here. I'm not going to write them out. I have 12 such individual, all those small pins that I made on my plot before. What I then do is that I define what is known as SSE, the error sum of squares, the sum of squares of errors. I take all of these numbers that I just talked about here. I square them. I compute for each individual observation within each group, and I add across the groups. Basically, I add all these 16 squared numbers. That's it, right? So I take this SSE in my example. That would be adding 2.8. Obviously, I'll not spend the time writing everything out. Plus this one squared. I have altogether 16 terms here because, 4, 8, 12. Sorry about that. 12 terms. 4, 8, 12. One for each observation. And the number becomes, I brought that, 5.195. That these are the two key computations to be made when we do analysis of variance. Of course, I'm not finished yet. We still have a little time to find out how to do all this. But the point is, these two computations are the key computations for telling the story here. Computing how much variability do we have within the groups, the error variability, and how much difference do we have between groups. And this is why we call it analysis of variance, because this is really the way we measure differences of groups is by means of a variability of group means, really. Question?
So, from the SSTR you got 30. Was that a big number or not?
We don't know yet. The question is this big or not? Yeah, well, I didn't give you the answer yet. It's a good question, and it's what we're going to get to in some minutes. It's going to be related to, in some way, we're going to relate it to this number, but we need just to think straight a little in exactly how we're going to relate those two numbers. Okay, this was the first initial part. We jump.